Hello everyone, and welcome back to another video where we're going to be evaluating this integral right here, which, like the day I just had, is very silly. So, without further ado, let's get started. What we're going to do to start simplifying is to express this denominator here as a series. So we know that we can express 1 over 1 minus x to the s plus 1 as just the sum from k equals 0 all the way up to infinity of x to the s plus 1 and then times k. And using this and subbing it in, switching out the order of the sum and the integral, we find the following. We see that we have x to the s plus 1 and then times 1 plus s to the s minus 1. So I'm just going to go ahead and distribute this now. Because it is a 1 after all, right? So we have an x to the s plus 1 and then plus an x. And writing all of this out, we have x to the s plus 1 times k, and then plus s, and then minus 1. All of this times natural log, of course. And then we have our integral from 0 to 1, and from 0 to 1, and then, well, I should probably write the arguments right there, and then our sum on the outside from k equals 0 all the way up to infinity, of course. And it's at this point that we can evaluate this integral directly, and then we just have to take care of the sum. So what we're going to do, zooming out and scrolling a bit down, is we see that we need to evaluate the integral from 0 to 1, generally of x to some, say like a, and then times natural log of x times dx. But this right here really isn't too awful. We can just do integration by parts, right? So evaluating this, we see that we have, well, if we integrate our x term right here, you see that we end up with a 1 over 1 plus a, and then times x to the a plus 1 times natural log of x. But then we also have the second part of our integration by parts, which is going to be our minus the integral from 0 to 1 of 1 over 1 over 1 plus a, times x to the a plus 1, but then we have the derivative of natural log x, which is just going to be 1 over x. So the a plus 1 just turns into an a, so we have x to the a dx, and we can just straight up integrate that, right? So our total result here, evaluating x from 0 to 1, given that the limit here, as x approaches 0 of x to the a plus 1 times natural log x, given that that is 0, I'll leave that to you to prove for yourself. Given that that's 0 for a positive a plus 1, we see that this whole first term right here is just 0 because natural log of 1 is 1, and that we're left with just negative 1 over 1 plus a all squared. So given that this is so, let's plug this into our integral real fast. So note that we're going to have two parts. Evaluating just the inside of our integral, that means our first a is just s plus 1. So that is a little bit of a whoopsies. That should be an x to the s plus 1 times k right here. But evaluating the inside of our integral right here, this means that this x to the s plus 1 times k term, this right here can just be thrown in as our a, right? So plugging in this s plus 1 times k as our a, we see that we have, well, inside of our sum, we have a negative 1 over, well, 1 plus a squared. So it's 1 plus s plus 1 times k all squared. And then we have our second one right here. And this time the plus 1 and the minus 1 and the exponent actually cancel. And what we're left with is a minus, of course, 1 over s plus 1 times k plus s, and then all squared, and our sum out front, of course. But you'll see that there's a similar structure to our sum. So let's try to get the k's on its own by factoring out from the denominator a 1 over s squared. So that way we can just have k on its own, right? So what this is just going to be negative 1 over s plus 1 all squared, and then times our sum again from k equals 0 all the way up to infinity of 1 over k plus 1 over s plus 1 all squared, and then plus this 1 over k plus s over s plus 1, again all squared. This is the part where I am going to reference our previous video, and one of the results of that video was our formula for the Digamma function, namely the following series: that digamma of some x is equal to negative Euler-Mascheroni constant, and then plus the sum from k equals 0 all the way up to infinity. I am reindexing the sum in this case, if you do go back and check. Instead, this is now 1 over k plus 1, and then minus 1 over k plus x. But you might see a parallel here, and that occurs namely when we differentiate this digamma function right here. If we differentiate this, right, so we have the derivative of the digamma function with respect to x, well, what we have is the Euler-Mascheroni constant is just, well, has it in the name. It's a constant, right? So that's going to go away. And so is the first term in our sum, actually. This 1 over k plus 1, that doesn't depend on x at all. So what we have instead is just the sum from k equals 0 all the way up to infinity. And actually differentiating this 1 over k plus x term with respect to x, we see that the minus sign goes away. And what we're left with is this 1 over k plus x, and then just squared. You see that we can actually express our sum in terms of a sum of digamma functions. But this actually is not crucially necessary to evaluate our integral, but it will lead to a very neat identity revealing itself later on. But turning our attention back to these sums, let's see what they're saying, especially these denominator parts, because they're awfully similar but only slightly different. So let's investigate this s over s plus 1 in relation to this 1 over s. Well, let's consider s plus 1, and then, 1 over s plus 1, and then just 1 minus that, right? What on earth does this equal right here? Why am I taking this digression right now? Well, I do just like digressing, first off. But second off, if we multiply the top and bottom of this 1 right here by s plus 1, getting a common denominator, you see that we have s plus 1 minus 1 over s plus 1, meaning that this right here is just s over s plus 1. So one way we can actually represent this sum right here, right here, specifically this term, is in terms of this right here. We can say that this term right here is just 1 over k, and then plus 1, and then just minus 1 over s plus 1. All squared. And, you know, we're summing from k equals 0 all the way up to infinity. But the important part here is that we can just reindex this and get this to be something much more symmetrical. Because we see that in our first term that we have a k plus 1 over s plus 1 all squared. And if we're able to reindex this right here, well, in that case, we can just have a k minus 1 over s plus 1. That's a plus. 1 over s plus 1, right? So in this case, what we can do is reindex this sum right here. And what we can do is just say now that the sum is going to start from k equals 1 all the way up to infinity, and then of just 1 over k, and then minus 1 over s minus 1. But in all honesty, I don't really like this formula starting at 1. So to make it just a little bit nicer, one thing we can actually do here is say this is the sum from k equals 0 all the way up to infinity, and then just minus the 0th term, right? So the 0th term here, would you plug in k equals 0, right? So that's just a 1 over negative 1 over s plus 1 squared, which is just going to be an s plus 1 squared, right? So this minus s plus 1 all squared. So grouping our terms and actually simplifying this into one big expression, this is what we obtain. This right here is the sum that we need to evaluate. But you'll remember that we actually do have a very handy dandy formula for evaluating certain sums. But the formula we have, at least on this channel, is from complex analysis. It's the one that goes from k equals negative infinity all to infinity. So what is one way we can actually make this work with that formula? Well, one thing you will notice, and this is very interesting, is that this right here is actually completely symmetrical. And so if you plug in negative k, that means that this right term right here, well, you're going to end up with minus k minus 1 over s squared plus 1. But you factor out the negative because of the squared, it just becomes positive. And the term on the left, you do the same thing. You have minus k plus 1 over s plus 1, but that right there is just equivalent to, because it is squared, k minus 1 over s plus 1. So at the end of the day, this actually is completely symmetrical, and because of that, we can use our sum formula to evaluate this. So let's go do that, shall we? As a reminder, our sum formula is this right here. So our sum from k equals negative infinity all the way up to infinity. I'll adjust for this sum being from 0 to infinity later. That's actually how we're going to take care of this term right here. But for now, we're just going to focus on this sum right here. So the sum of this right here, where that is the same argument as this right here, right, is equal to negative pi times the sum of the residues of cotangent of pi z times our function right here, which I'm just going to rewrite in terms of z, right? So we're going to have 1 over z plus, for brevity, I am just going to call this a right here, just because it is a lot to write 1 over s plus 1. So we're just going to have this and then plus z minus a right here, all squared. So now all we have to do is evaluate the residues of this right here, but at the poles, you'll remember, of our f, of this function right here. So what we're going to do is evaluate this at the residue, or find the residue of this whole function right here at z equals a, and also z equals negative a. But what we will actually see is the two end up being the exact same, which is a bit funny, but I'm getting ahead of myself. Let's get evaluating, shall we? So by the formula for a residue, what we have is, because it is these poles are second degree poles because we have the squared right here, what we actually have is going to be the derivative, so d over dx, of this right here, our cotangent of pi z, and then 1 over z plus a squared, and then plus 1 over z minus a squared. And then, of course, we have to multiply this by either z plus a or z minus a, both squared, obviously. So let's just start with the positive one, the positive pole, so z minus a, right? So that means this term right here, this is just going to be 1. So kind of erasing that, we're just going to have plus 1. And then in the numerator here, we're going to have a z minus a all squared. So z minus a squared. And the limit, of course, as z approaches a. So to evaluate this derivative, we can just use the product rule, really. Just do that real fast. And here's what we end up getting. The derivative of cotangent of pi z is actually just negative cosecant squared of pi z, and then by chain rule, an extra pi, right? So this right here is just going to be minus cosecant, or really minus pi. I'll make that minus sign into a pi. That works. Minus pi cosecant squared of pi times z, and then times our big function right here. So z minus a all squared over z plus a squared, and then plus 1, of course. And then what's the derivative of this right here? So we have a plus, of course, times cotangent of pi z. Well, what exactly is the derivative of this right here? Well, the derivative of a constant, the 1, doesn't matter. It's just going to be 0 anyways. So we just have to focus on the derivative of that whole thing right there. And if you remember the quotient rule, it's low d high minus high d low, square the one that's down below. You see that if we plug in a, right, the numerator right here is z minus a squared. And if we plug in a there, it's just going to be 0 because, z minus a all squared is 0, of course. But if we consider its derivative, that being 2 times z minus a squared, well, it's still going to be 0. Or sorry, 2 times z minus a, not squared. I mean, either way, it's 0. That's the point. So this whole term right here is actually just going to be a big 0. I'm not going to evaluate the derivative of that. I'll leave it to a proof to the viewer. But really, it is quite simple, especially because the denominator right there is just z plus a squared. So only focusing on this term right here, we need to plug in z as it approaches a. And you'll see that this right here, this term right here, completely just goes to 0 because, again, a minus a is 0. Groundbreaking math we're doing on this channel today. We discovered that a minus a is 0. But that leaves us with the residue being equal to minus pi times cosecant squared of pi and then times a, because we plugged that in. Do note that if you plug in, if you did the residue of minus a right here, so z plus a, you would end up getting the exact same thing. And one of the reasons for that is just because the cosecant right here is just squared, right? So even though it is an odd function, you plug in negative a into here, you end up with the same result. So truly the sum of our residues, is equal to 2 times this. So let's plug that into this formula, shall we? We now have that our sum from negative infinity to infinity is equal to, well, the minus signs cancel, and the pi's we can combine into a big pi squared, and then times a cosecant squared of pi and then times a. But remember that this is a sum from k equals negative infinity to infinity. And what we truly want is a sum from negative, or sorry, I guess I can make that work, negative 0 to infinity. But what we want is a sum from 0 to infinity. So writing this out, this right here, sorry, this should be an extra 2. This right here is, equal to the sum from k equals 0 all the way to infinity. But then it's also, we have this other part, right? The sum from k equals negative infinity all the way up to 1. But we also know that it is going to be symmetrical, right? So if we, this would be negative 1. If we add what this sum is at 0 and then subtract it, we can just make use of symmetry and say that this right here is equal to this, right? So actually doing that, plugging in 0 into this whole thing right here, we see that we have a 1 over s plus 1 over s plus 1 squared, and the same things. So really what it is 2 over, we have both a plus and a minus 2 over, 1 over, so really it's 2 and then times, so 2 times s plus 1 all squared. But then we have, minus that, so 2 times s plus 1 squared. And combining these terms right here, we see that we have the sum from k equals negative infinity all the way up to 0. But by symmetry, we do know that this right here is just equal to the sum from k equals 0 all the way up to infinity. So really what we have is 2 times our sum from k equals 0 to infinity is equal to 2 times s plus 1 all squared, and then plus 2 pi squared times the cosecant squared of pi and then times a, but our a right here is an s plus 1. And dividing by 2, we see that, well, all the 2's really go away. So we have, let's see, getting the red marker, boom, bang, bop. They all go away. So actually plugging this in to our original formula, we see that we have, so our original formula being this right here, we've just evaluated the sum. So all we need to do is take our sum, subtract s plus 1 squared from it, and stick a minus 1 over s plus 1 squared term out front. So using the results of the sum right here, we see that we have s plus 1 squared, and then plus cosecant squared pi over s plus 1. But then we will remember that we also have this minus s plus 1 squared. So these terms actually just completely cancel. And there's a pi squared up front, I do apologize. And then you will remember that we have a minus 1 over s plus 1 all squared right here being distributed. Thus, our answer right here is just going to be minus 1 over s plus 1 all squared, and then times pi squared, or I'll throw the pi squared actually at the numerator right here, so pi squared times cosecant squared of pi over s plus 1. And that right there, ladies and gentlemen, is our result. Now, as promised, there is one interesting note right here with the digamma function. And that right there is that this right here, we saw that this right here can be expressed as a digamma function, right? So if we look at these two terms right here again, right, comparing them with our definition for our digamma function, or derivative of our digamma function in terms of its sum, we see that we have, this could just be expressed as digamma of 1 over s plus 1, and then plus digamma of 1 minus 1 over s plus 1. And what we've effectively proved in this video, at least, is that this right here is equal to pi squared times the cosecant squared of pi over s plus 1. This right here is what we proved in this video, which is a fun little thing to prove. It's a really neat identity. Or sorry, I do apologize, this is the derivative of that digamma function. But at any rate, I hope you all enjoyed this video in a continuation with the digamma stuff, and I will see you all in the next one. Maybe we'll do some Euler's or Lagrange stuff. That'd be fun. At any rate, bye! Hold on 1 second. The recording needs to stop. Recording needs to stop. Stop.